Welcome to Buckeye Turf Podcast. My name is Carl Danneberger, Professor of Turfgrass Science at The Ohio State University. The topic of this podcast is water use, specifically turfgrass water use rates. Turfgrass water use rate is defined as the total amount of water needed for plant growth, which includes water loss by transpiration and evaporation from soil and plant surfaces. Water use rates, also referred to as evapotranspiration or ET, are expressed in terms of inches or millimeters per day. The factors that influence turfgrass water use rates include 1. The evaporative demand of the air surrounding the turf, 2. The quantity and quality of water with which each turf is supplied, and 3. The transpiration and evaporation levels typical of that turf and soil in response to evaporative demands. The driving force for evaporative demand is solar radiation. Solar radiation is influenced by climate, season, altitude, and latitude. The impact of these factors, along with others, will be discussed in further detail later in this podcast. The solar energy that is absorbed by the turf can be dissipated in several ways, including through latent heat of evaporation, which is transpiration. The water use rate, as previously mentioned, is the evapotranspiration or ET rate of the turf, which is both plant transpiration and soil evaporation. For calculating the water use rate of turf grasses, the assumption is made that sufficient soil water is available and will not be a limiting factor for transpiration. Measuring turfgrass water use rate starts with calculating the evaporative demand. A simple method for determining evaporation is by using evaporation pans. The best known of the pans are the Class A evaporation pan. Daily, or whatever time period used, measurement in the drop on the pan water level is evaporation. The most well-known means of estimating water use is known as the Penman equation. The Penman equation uses a combination of mass balance and mass transfer principles to calculate water loss. Those variables are listed here. In both the pan evaporation method and the Penman equation alone do not estimate water loss or ET from the turf. The evaporation data needs to be adjusted using a crop coefficient or Kc value. Crop coefficient uses the potential evaporation of the turf or water use rate and the actual evaporation calculated. The crop coefficient is normally less than 1 and ranges depending on the species and cultivar, and usually is from 0.6 to 0.9. The crop coefficient is influenced by the turf's growth stage, environmental conditions, and cultural management programs. As an example how Pan A evaporation data and a crop coefficient are used to estimate the water loss from the turf, the equation ET, or evapotranspiration, equals the crop coefficient times the open pan evaporation data. Given a crop coefficient of 0.8 and an evaporation of 0.3 of an inch, the water loss was 0.24 inches per day. Let's look at some of the factors that influence the water use rate of turf. Previously, solar energy was mentioned as a driving force for transpiration. At the equator, you would think that the solar radiation would be the highest, but along the equatorial belt, solar radiation is scattered due to cloud cover and high humidity. The belt roughly 15 to 35 degrees north receives up to 90% direct radiant energy and has little cloud cover. Above the 35 degrees is less favorable because of the greater amount of solar energy that is scattered. This photograph from NASA shows the intensity of evaporation on a global scale. The purple regions have the lowest evaporation while the red regions the highest. The zones are shown over the oceans and seas of the world, obviously the areas where evaporation rates would be high. Turf environments that are hot and dry will have the highest ET rates. This table provides the potential evapotranspirations for various climatic situations. Altitude can play a role in water loss. Higher altitudes tend to have higher evaporation rates due to lower atmospheric pressure. The length of the growing season influences water use rates. The longer the growing season, the higher the annual water use rate of the turf. The highest water use occurs when the turf is actively growing, usually late spring through early to midsummer, and is the lowest in winter. The season in certain regions can be artificially increased by winter overseeding. For example, where Bermuda grass may normally go dormant, as shown here on this golf course fairway, but by overseeding, the seasonal water use increases because of the presence of the growing of the cool season turfgrass. Water use rates vary among turfgrass species. This photograph is of creeping bentgrass greens surrounded by Bermuda grass. When directly comparing water use rates between cool season turfgrasses and warm season turfgrasses, cool season turfgrasses have a higher water use rate. It should be noted that water use rate does not equal drought tolerance, but a low water use rate can delay the onset of drought. It can be an important factor when designing an irrigation system. Cultural practices like mowing impact water use rates. The higher the height of cut, the higher the water use rate. Generally, turfgrasses that have more vertical leaf orientations and high leaf extension rates have higher water use rates than grasses with horizontal growth habits and limited leaf extension rates. Mowing frequency can affect water use rate. Sherman and Beard demonstrated that increasing the mowing of creeping bentgrass from 1 to 12 times in a 14-day period increased water use rate by 15%. Thus, more frequent mowings, especially on greens, most likely will increase the water use rate. Turf subjected to increased traffic or wear have higher water use rates. Certain diseases, like rust, can increase water use rates. Rust pustules that can rupture the leaf epidermis, creating water loss. With water becoming more limiting, an understanding of turf water use rates is important in turfgrass selection and designing irrigation systems.